We're going to go on now to another analytic technique. In fact, the last one to do with analytic techniques. So I'll show you again the list that we had to begin with. See where we are now. We've done all of the top ones down to the improved formulas for quadratic roots, and we've jumped ahead and done the extra element theorem next. Now, the next one we're going to do is the input-output impedance theorem. And I talked about the motivation for this earlier on. It's the similar sort of motivation for the extra element theorem, which is, it's really just a way of saving work, or making a derivation simpler and shorter, which is better in all respects. So I'll review quickly the motivation for the input-output impedance theorem. There's a green box representing just a general linear system as usual. A general source, the Thevenin equivalent, Vs series with Zs, generalized load, Zl. The most important quantity we're usually interested in is the voltage gain Vs to Vl. And that's where most of the work is. And even if you adopt all these techniques we talked about up to now, it's still where the bulk of the work resides. But often you need to know also what the input impedance of the system is in order to meet some specification to do with that. And the conventional way of going about it is that after you've done all the work to find the A, getting it in fact in pole zero form, sketching asymptotes and so on, you've got to do it all over again to find the Zi. Because the Zi is a different transfer function for the same system. The Zi is the input voltage divided by the input current. So usually you go back to your circuit model and you start all over. And if there is feedback in the system, that is just about as much work as the first calculation was to find the A. And the same thing is true also if you need to calculate output impedance. To calculate output impedance, the way you usually go about it is you make the input 0, you apply a separate source at the output, and you calculate the ratio of VL to IO under conditions of zero input. That's basically the definition of output impedance. And especially if there's feedback in the system, again, this is just about as much work as the first two calculations. And so you end up doing 3 separate chunks of work which are more or less equally lengthy. And when you've done that a few times, you begin to notice that several of the segments of those 3 chunks of work resemble each other. There's a lot of similarity. You find yourself going through the same sequence of steps. But of course it's not all the same, and you get the idea there ought to be a shortcut to this. There ought to be some way of avoiding the repetition of the parts of the derivation that are the same between the 3 answers and doing only the parts that are different. But that's as far as you get, because you don't know how to separate what's the same from what isn't. That's the motivation for the input-output impedance theorem, because that's exactly what its purpose is, and it's exactly what it does. It allows you not to repeat the parts of the calculation that are the same. Okay, that's the motivation. Now I'm going to derive the theorems, and that won't take very long. First thing is, go back to our generalized model. We'll do the output impedance theorem first. And the first thing I'm going to do is take a special case of the output connection. I'm going to let the load impedance go to infinity. In other words, it's unloading the output, or it's open circuiting the output. And I'm going to ask, what is the open circuit output voltage that I see when I've done that? And so what I'm going to see is the voltage of this Thevenin equivalent generator at the output. Because if I unload the output, the load current goes to 0. There is no drop in the output impedance. So the output voltage is equal to the generator voltage. So this is simply a matter of introducing notation. VL under the condition of ZL go to infinity simply means the open circuit output voltage, and it's equal to kVi. Set that result aside. Go back to the general case and make the opposite extreme condition. Short circuit the output and ask what is the current that flows through the short circuit. And the notation is IL under the condition of ZL go to 0 simply means the short circuit current. And what is it? Well, it's equal to the value of this Thevenin generator divided by ZO, the output impedance, obviously. Then what you do is you divide the first result by the second one. And what happens is, if you divide kVi by kVi over ZO, the result is ZO, which is the output impedance that we're trying to find. And what it's equal to is the open circuit voltage divided by the short circuit current. Well, big deal. That's nothing new, is it? It's almost a definition of output impedance. Because this sort of interpretation that we've just gone through, limiting the output to be open circuit voltage or short circuit current, well, this is what you'd expect. So there's nothing new there. But there's one little extension. That's all we need. The output impedance is open circuit output voltage over short circuit output current for the same input voltage. That's a necessary condition for that to be true. It's easy to see why. Because we've got to cancel the VI. If you don't keep VI the same for those two conditions, it doesn't cancel. So this is a necessary constraint. And of course, for the same VI, you also have to have the same VS. So what I wrote in red there is an important condition for this statement to be true. You have to calculate the open circuit voltage and the short circuit current for the same input. And that's the condition that you use to get the useful result of the theorem. Because all that we have to do now is divide that same input voltage into both the numerator and denominator of this result. So here's the same thing again. Output impedance is open circuit voltage over short circuit current, and I divide the VS into both of them, and I make one other substitution. IL, in general, is VL over ZL. That's where we started. So I make that substitution also in the bottom line. And what I've got now is I've got VL over VS in two different places, but VL over VS is the voltage gain that I already have solved for. And that's the theorem. Nothing to it, is there? Couldn't be much simpler than that. So, since you already know what the voltage gain is, to find the output impedance, all you have to do is take these two simple limits. And you can do that because the ZL is inside the A, because it's there when you calculate the A. So taking the two simple limits represents the only additional amount of work you have to do to find the output impedance over and above the work you've done already to find the A. And even without trying it, it's pretty easy to see that there's not much involved in doing that. So that's the output impedance theorem. Okay, there's an input impedance theorem. You're beginning to anticipate pretty well by now that duality helps a lot with these things. So, the derivation of the input impedance theorem follows the same sort of argument. We do some work at the input end now instead of the output end. The first thing we do is we say, let's let the source impedance go to 0 and ask, what source voltage do we have to apply in order to get a certain value VI at the input to the system? And again, this is to introduce notation. Vs under the condition of Zs going to 0 is simply the notation that says that's the input voltage you need. And of course it's equal to the VI that you want to get. Then you go to the opposite extreme. Visualize replacing the Thevenin source equivalent by a Norton equivalent, which would be a current generator, Vs over Zs, in parallel with Zs. That's the Norton equivalent. Then let the parallel Zs go to infinity and ask, what current do you have to apply from the Norton source in order to get the same voltage at the input to the system as before? So the value of the Norton current that you have to apply, Vs over Zs, under conditions that Zs now goes to infinity, the current you have to apply is obviously equal to Vi over Zi. And you divide one answer by the other, and the VI's cancel, and you're left with Zi is equal to the input voltage divided by the input current that gives the same value of Vi. Again, the same Vi is a necessary condition, otherwise it doesn't cancel out. But if you have the same Vi at the front end of the amplifier, regardless of whether you've driven it from a voltage or a current, then of course you get the same output voltage as well. So you do the same trick. You divide the same output voltage into both numerator and denominator of that expression. So here's the starting point. The input impedance is the input voltage divided by the input current to get the same VL, and I divide VL into both of them. And now, once again, I can recognize VL over Vs in two places, which is the original voltage gain we already know, and you just get rid of the internal fraction and bring this one up to the top, and that's the answer. And it's very similar to the output impedance theorem, which says you've done all the work already to find the A, and then to find the input impedance, all you have to do is take two simple limits. And the Zs is inside the A, because the Zs was in the model when you solved for it. It's almost too good to be true, isn't it? I mean, it's just ridiculously simple. And as usual, when I get to this point, I like to ask everyone, have you ever seen this before? No? Isn't in the textbooks, is it? I think this is an even clearer motivation than it was for the extra element theorem. Because, you often have to calculate input and output impedances, and everyone does it the hard way. Applying a signal at the output and finding a current that goes in and all that, and same thing at the front end. And you get to go through all that nice algebra over again. Well, you don't have to. And these theorems look a little odd because you don't normally think of formulas involving these limits. But you know how to take limits, even though you may be rusty on it, because that's something you learned to do in math. That was the foundation of calculus, if you remember. But you never used that again. So all you've got to do is brush the dust off some of these old techniques that you really know already anyway, and that's all you need to use these nice simple results. Now, when I was talking about the extra element theorem, I said I developed this a long time ago, and I was reluctant to publish it because I was sure it must have been done before. So I procrastinated on that for a long time. Now, as far as these input and output impedance theorems are concerned, I know they've been published before because I wrote the paper. And it was presented at the National Electronics Conference in Chicago in 1963. Sank without a trace. Which goes to show that even if things do get published, they still may not find their way into the textbooks. I don't quite know what it takes for that to happen. There's a lot of luck about it, I suppose. Well, eventually I suppose I will, but I've got involved with a couple of other books before, and I don't want that millstone around my neck for a while yet. Anyway, this is almost an extreme example of a very simple formula which is very useful and yet somehow hasn't been adopted. Well, there's a little more to do about it than that. What we've derived so far is a pair of formulas for calculating what I call inside input and output impedances. Inside in the sense that they are inside the source and load relative to the box, which is the amplifier we're talking about. That means that you could also define outside input and output impedances. I put a prime on them. Put a prime on them to distinguish the two. Obviously, Zi prime is equal to Zs plus Zi. Obviously, Zo prime is equal to Zl parallel Zo. So why do we need to say anything more about it? Well, because these are very nice simple formulas, but when you come to apply them, they're not so simple. Because both of them involve a summation. This is product over sum. So if you start knowing what the Zi and the Zo are, and the Zs and the Zl, in factored pole zero form, and you want to find what the outside impedances are, then you have to perform a summation of factored pole zero functions, which means cross-multiplying numerators and denominators, collecting powers of S into a new polynomial, and refactoring a new polynomial. And that's messy. So even though the formulas are very simple, the application is not so simple. So this gives you another motivation. Maybe we can find some modified formulas for the outside input and output impedances directly from the gain, which wouldn't involve the intermediate summation. And in fact, you can do that. And here's the result. So here are the original formulas for the inside quantities. Here are the corresponding formulas for the outside quantities. And perhaps you say, well, fine, but this is black magic. Where did they come from? So I respond to that. I don't have to derive them. By a few sentences of sort of hand-waving argument, I think I can convince you that these are the right answers, as follows. If you want to find the outside output impedance of the green box, which is the objective, all I have to do is invent another box, a blue box. And the only difference is that the ZS and ZL have gone inside the blue box. And now all I do is apply the original formula to the blue box instead of the green one. And remember, all that the original formula for the output impedance says is output impedance is equal to the open circuit voltage divided by the short circuit current for the same input. What is the open circuit voltage of the blue box? VL. It's already open circuit because it doesn't have any external load. It's already open circuited. The numerator of the formula simply came from the original open circuit output voltage divided by the VS. So if it's already open circuit, all I have to do is take the output voltage without the limit and divide it by VS. So VL over VS for the blue box is simply the original loaded gain of the green box. You don't have to take the limit. The denominator of the original formula simply says it is the short circuit output current. But the short circuit output current of the blue box is the same as the short circuit output current of the green box. So the denominator stays the same. So the only difference is to find the outside output impedance of the green box, you simply identify it as the inside output impedance of the blue box, and the only difference is you don't take the limit. You don't let ZL go to infinity. And the argument, of course, is similar for the input impedance. The outside input impedance of the blue box actually arises from the input voltage divided by the input current to give you the same output. The input current of the blue box is the same as the input current of the green box. So the term that corresponds to that input current, which is this one in the numerator, stays the same. The only difference is the input voltage of the blue box already has no external source impedance, so you don't let ZS go to zero in the corresponding term. The external source is already zero for the blue box. So by using that intermediary of the fictitious blue box, I've established that these are the right formulas for the outside impedances of the green box. So now we have two sets of formulas. In fact, you notice something else very simple about this now. The formulas for the outside impedances are simpler than those for the inside impedances, because only one limit is required instead of two. Things get better and better. Which means that in retrospect, we really ought to reverse the order of those two expressions, because regardless of which impedances you want to find out, it's always easier to calculate the outside ones first, because only one limit's needed. And then you can calculate the other ones by taking the other limit in the answer you've got already. Because the limits are independent. It doesn't matter which order you take them in. They're separate calculations. So you can take one set of limits to find the outside impedances. Then you can take the other set of limits in the answer you got already, because whether you do it in succession or whether you do it at the same time doesn't make any difference. So you might as well get a free set of answers along the way anyway. Both of those emphasize why these formulas are so easy to use. Because you have A in factored pole zero form, which means you take these limits factor by factor, separately. Which says that you automatically get the answers for the impedances in factored pole zero form. So everything's on the positive side for using these formulas. If you start with a low entropy expression for the gain, you automatically get a low entropy result for the impedances. And the steps involved are trivially simple. So let's look at an example. Again, this gives us a chance to back up a little bit and practice some of the previous techniques in order to get to the starting point, which is the voltage gain of the system. So let's begin with a little more elaborate linear amplifier now, which consists of the common emitter stage that we've talked about ad nauseam already, and put an emitter follower on the output. The first thing to do is calculate the most important parameter, which is the voltage gain of the system. So let's review that again, just to check out some of the techniques we've done already. Okay, the first thing is to substitute for the transistors the simple equivalent circuit model that we've used already. So what that does is this. So the first transistor is replaced by the collector current generator and emitter resistance. So is the second one. And the power line AC ground is brought down to the bottom. So now we can get rid of the original and work in terms of this model. As a passing comment, notice that the model of the first transistor is the one we've used all the time. The model of the second one is the same, but the current direction arrows are reversed. That does not mean it's a PNP transistor instead of an NPN. It isn't. They're both NPNs, as you saw in the original model. The direction of the arrows is arbitrary because this is a small signal AC model anyway, and you can choose whatever reference direction you like. The only requirement is that you have a consistent directions between the dependent quantity and the independent quantity. So if I reverse the base current, I'd better reverse the collector current as well. And the only reason for doing that is a very minor convenience, which is that if I take the original voltage V1 to be positive, IB1 is positive, so is the collector current, which means that the IB2 will be positive in the reverse direction because of the phase inversion of the first stage. And that's not a necessary choice. It's just that it's a little more convenient to have all of the defined quantities positive at the same time. But you don't have to do that. And for the same reason, I define the output voltage with a minus sign in front, which I already did for the output voltage of the single stage. It just accounts for the phase reversal, so that the voltage gain comes out as a positive quantity, because the minus is kept explicit. Okay, now the objective is to find V1 to V4, the voltage gain. And once again, you've got a wide range of choices about which techniques to bring to bear on this. Some of them involve circuit reduction by doing the algebra on the diagram. Some of them involve techniques like reflecting emitter resistances one direction or the other. Some of them involve current and voltage dividers. Some of them involve strictly algebraic techniques. You take your choice. So I'll select a particular sequence just as an example. And the first thing I'm going to do is reflect the RE1 into the base in order to separate the input circuit from the rest of it. So when I make that substitution, this now becomes 1 plus beta 1 RE1 in the base, and it's gone from the emitter. That makes no difference to the collector generator because it's an ideal current generator anyway. That's the first modification. The second one is I now have two loops in the middle because I have what amounts to a Norton equivalent. I have a current generator in parallel with R3. I can get rid of one of the loops by using Thevenin's theorem. Again, one of the basic techniques. Reduce the number of nodes and loops. So I'll replace the Norton with the Thevenin, which gives this. So now the R3 is in series with the corresponding voltage generator. Well, I'm bored with the circuit reduction now, although obviously we could continue it further. But I'll just change over and continue the rest of it analytically, just as, again, as an example. So the overall gain, V4 over V1, can be broken up into these intermediate fractional gains. V4 over V Thevenin is found simply from this rather more complicated voltage divider, which is the bottom branch, R4 parallel RL, divided by the same thing plus the top branch, which is RE2 plus the reflected R3. So the last fraction represents the voltage divider V Thevenin to V4. The factor in front is V Thevenin in terms of IB1, which is simply the value of that generator. That gets us back to IB1. IB1 can be found as a current divider from I1. That's the first factor. Remember that from earlier on. A current divider is found by the opposite branch divided by the sum of the branches. Finally, I1 is found from V1 by the total resistance of the input loop, which is this second denominator. So that's established the overall voltage gain in a low entropy form because all the impedances appear either as ratios from dividers or as series and parallel combinations. When you substitute the numbers, you find that the first factors end up at being 62, which is essentially the same as it was for the first stage by itself, because the voltage gain of the emitter follower is almost unity. 0.98 in this case. In fact, that's one of the purposes of the emitter follower. Emitter follower gives you a big current gain, but it doesn't give you any voltage gain. It's sort of like half a transformer. Transformer transforms both voltage and current according to the turns ratio. A transistor transforms current by a large factor, but voltage 1-to-1 almost. Which is why impedances reflect according to the current gain and not the ratio squared. See, you're used to reflecting impedances through a I better not say that, haven't you? Because you don't like transformers anymore. Anyway, you may remember that you can reflect impedances between primary and secondary of a transformer according to the square of the turns ratio, which is really the product of the current and the voltage ratios, but a transistor reflects it only according to the current ratio. So it's not the square of beta, it's only beta, or 1 plus beta. Okay, well now we've got to that point. We've found the voltage gain in a low entropy form. In fact, it's in a factored form. So we're now ready to apply the input and output impedance theorem to find those impedances for this particular example. So to simplify the notation, I've crunched those factors from 4 down to 3. and I've simply identified them as K1, K2, and K3 in order to avoid writing it all out each time. Let's calculate the output impedance first, and we already know that it's going to be easier to calculate the outside output impedance first, because only one limit is required. So here's the theorem. We want to find ZO prime. First thing we do is recognize that the whole model is resistive, so the output impedance is an output resistance, so we'll identify it as such by putting the sub M on from mid-band again. And the theorem says we can find ROM prime by taking the voltage gain as is, which is the AM, and dividing it by the voltage gain over ZL, but ZL is RL, and letting RL go to 0. The voltage gain is K1, K2, K3, so you substitute that numerator and denominator. And having done that, immediately you see a giant simplification. Any factor in the A that doesn't contain RL is unaffected by the limit and cancels out. So when you look at K1, it doesn't have RL in it. So in the denominator, when you let RL go to 0, it doesn't change K1. So it cancels the one that's in the numerator. And the same thing for K2. K3 is the only one that does have RL in it. So when you take the limit, it's going to change. So it doesn't cancel, but that's the only thing you have to keep. Now, that always happens. So immediately, most of the stuff in the gain goes away. Okay? Well, work on what's left. Find the limit. K3 is this ratio, and in the numerator, now finally is the time to multiply out product over sum. The denominator stays the same. We have to divide it by RL, and then RL that we're dividing into it cancels the RL that's inside the K3. Then you let RL go to 0 in what's left, and in the numerator, having cancelled RL goes to 0, you're left with R4 over R4, which is 1. And in the square bracket in the denominator, you let RL go to 0. That kills this parallel combination, and you're left with a series added term. So that's the result for the limit. So now you plug back into what's left of the theorem. Squeeze it all in there. Plug it back into the theorem. So now you have the original K3 as before, divided by the limit that we just calculated. So this square bracket comes up on top. And that's the answer. Well, you can lower the entropy a little bit by recognizing in a rather obscure form product over sum, which is parallel combination of R4 and RL already in the parallel combination times the square bracket, and it's divided by R4 parallel RL plus the square bracket. So you can condense that down to the triple parallel combination. When you substitute numbers, R4 is 10K, RL is 10K, the RE2 is 30 ohms, the reflected R3 is 60 ohms, Add the two together, you get 90 ohms in parallel with 5K. The 5K doesn't do anything, and you're left with the 90 ohms. Well, as usual, when we're practicing a new technique, we do it first on a very simple example, such as this one, in which the answer is obvious anyway. Because it's easy to see by looking in at the output that the outside output impedance is R4 parallel RL parallel RE2 plus the reflected R3. Because if you were to derive the output under conditions of 0 V1, that's the answer you would get. And because the V1 would be 0, this generator would be unactivated, and so the output impedance doesn't get any further back than the R3. So in this case, you don't even need the theorem because the answer is obvious anyway. But nevertheless, it's a good way to practice using the theorem. Of course, the result is what you expect from an emitter follower. That's one of the reasons for using an emitter follower, is to give you a low output impedance. And you see, the reason it's low is because of its reflection property. Whatever impedance there is in the base appears in the emitter divided down by the 1 plus beta. Add that to the RE that's there anyway, and that path has a much lower impedance than the external load itself does. Okay, to continue with the application of the theorem, suppose you want the inside output impedance. That means taking the other limit in the answer we got already. So we take the outside output impedance we just found, and you let RL go to infinity this time, which is obvious from the model. If you let RL go to infinity, it simply transforms one impedance into the other, which in this case, of course, simply takes away the paralleling effect of the RL. Since that wasn't doing anything anyway, numerically the answer isn't any different. So it's very easy to apply the theorem. Let's do the same thing for the input impedance. Again, this is the mid-band result, so we'll change the symbol appropriately. Mid-band input resistance. The theorem says we substitute for the AM both numerator and denominator as K1, K2, K3. The same giant simplification. Any of those factors that doesn't contain RS cancels out because it's unaffected by the limit. K1 doesn't have RS in it. K3 doesn't have RS in it. They go away. K2 does have RS in it. So it stays. And that's all you have to work on. So, determining the limit, K2 is the middle fraction, multiplied by RS, and let RS go to infinity. So the denominator goes to infinity, and you drop the rest of it. That allows RS in the denominator to cancel the 1 in the numerator, and you're left with beta 1 R3. And the final line, plugging into the limit, the input resistance is the original, is the limit we just found, divided by the original K2. Some more things cancel and you rearrange, and that's the result. And again, this is a simple enough case that the answer is obvious anyway. The outside input resistance is RS plus RB parallel the reflected RE1, which is exactly what you get out of the theorem. If you want the inside input resistance, you just let RS go to 0 in the previous answer, which of course simply takes away its additive effect. So that shows you how easy it is to apply the theorems. Of course, these examples have been a little too simple. So after we come back from lunch, we'll modify it a little bit and we'll put some reactances in there and see how you deal with the theorem when you have a frequency response involved. And it won't be much more difficult. So let's start up again around 1 o'clock. Well, so far we've seen for the application of the input-output impedance theorem, applied it to a very simple case where everything was resistive, so there was no frequency response involved. So now we'll apply it to a slightly more complicated case. And we'll start with the same basic model that we've had already, but since that's mid-band, in order to put some frequency response into it, we get to review the extra element theorem again, because that's how we'll put some capacitors in to see what the influence is on the input and output impedances. So starting with the same model that we've already had for the common emitter and emitter follower stage, let's put in some simple frequency dependence in the form of the emitter bypass capacitor. So we now want to discuss the circuit where we have the external emitter stabilizing resistor and the bypass capacitor C2. So this is a good opportunity now to use the extra element theorem again to put the capacitor in. And it'll give us, since we've done this problem before, in fact twice, we'll do it a third time, again using a slightly different approach. What we did before for this particular problem to modify the gain to account for the bypass capacitor was we started without the capacitor but with the resistor. That was the first example of the theorem. What we did then was we started without either one of them, and then we put the two in together as a series element, which is when we found out that the theorem applied equally well to any network of elements, not just one of them. Now we'll do the same thing, starting again from a slightly different position, and that is we've got the mid-band gain in which both of them are absent, but we can count only the C2 as the extra element, simply by considering the reference condition to be when the extra element is a zero impedance. Because when it's a zero impedance, it bypasses out the resistance anyway. So we can still use the mid-band value of the gain as the reference condition, and yet use the capacitor by itself as an extra element. Now, this time, I won't draw any intermediate diagrams or write down any intermediate equations. We'll do it all mentally now, just by visualizing the intermediate steps. So, the reference condition is when the cap is a short, which kills the resistor automatically at the same time. So the reference gain is AM as we have before. So all we have to do is find the two driving point resistances. So the RD is found by replacing the capacitor by an independent source, making the original input zero, and finding by single injection what the driving point resistance is, seen in place of the capacitor. So by inspection in this case, if you look in from the capacitor, you're going to see R parallel RE1 plus the reflected RS parallel RB. So that's the RD. We already know the RD is going to determine the pole frequency, omega 2. So the pole is C2 together with the RD that we've just calculated. So that's half of it. The other half is the zero is going to be determined by the same capacitor and the Rn. To find the Rn, replace the capacitor with the independent second source, restore the original input, imagine that you twiddle the two of them to null the output. propagate the null back to the second source and see what happens to its current. So if you propagate the null backwards, everything has to be null all the way back to the collector of this transistor and therefore the emitter as well. And once again you end up with the requirement that the emitter current is 0 if the output is null. Therefore the impedance seen looking in is just R. So the Rn is R. And that identifies the 0. We know the pole and the 0 are going to be in inverted form because the reference gain is the high frequency limit. So the correction factor is of the form 1 plus Zn over Z. The Z is in the parallel combination. So that's how you can write down the factored pole 0 form in the answer, by doing the entire application of the theorem mentally. Well, now we've reviewed that. The next step is to see what happens to input and output impedances. So we'll go back to the outside output impedance again. Apply the theorem for the outside output impedance, applied now to the modified A, including the pole and the 0. But that includes the AM as the factor in front, and we've already solved the problem for AM by itself. And that doesn't change, because when you take limits, you do it factor by factor anyway, so the previous result we got for AM remains unaltered. Namely, the K1, K2 cancel out, the K3 doesn't, and we've already solved that part of it. Now, the only additional thing is we have a pole and a 0 as well, but they are just additional factors. And the same consideration applies to those as to the K1, K2, K3. They're just factors of A. Therefore, any factor of A not containing RL is unaffected by the limit and cancels out, and that applies to corner frequencies as well. So when you look at the 0, it doesn't have RL in it, so it cancels. Not only the corner itself, but the entire factor. And the same thing with the omega 2. That doesn't have RL in it, so that cancels, or I should say its entire factor cancels. So in this particular case, the corner frequencies disappear and they don't affect the output impedance. There is no frequency responsive output impedance, which again in this particular simple example of course is really obvious, because when you look back in from the output impedance is contributed by elements back to R3, and what happens before that doesn't get into the game anyway. So it makes no difference whether the C2 is there or not. The cancellation of the corresponding factor is the way that shows up in the output. The C2 has no effect. So that was kind of a false start. This problem turned out not to be more complicated after all. So let's make another try. Let's go back to the input impedance in the presence of the capacitor. Now obviously the capacitor is going to have some effect because it's part of the input loop. So going back to the input impedance theorem now, starting with the modified gain, including the inverted pole and 0. Now we apply the theorem to the modified A, and again the midband part of it stays exactly the same. So we don't have to deal with the K factors again, we've already done it. All you have to do is look at the remaining factors and follow the same process. And you look to see whether the RS is inside either one of them. Well, the RS is not inside the omega 1, so the entire inverted 0 factor, including omega 1, cancels. But this time the RS is inside the omega 2. So it will be affected by the limit, so the pole factor does not cancel. But that's the only one you have to work on. So what happens? There's an omega 2 in the denominator that remains as is. That comes up into the numerator and stays. So the only new thing you have to work out is omega 2 as RS goes to infinity. But here's the original omega 2. If you let Rs go to infinity, it just takes away its paralleling effect. So what happens is you get the original omega 2 factor in the numerator, and you get a new factor in the denominator involving a new corner frequency, but one that is obtained from the old one by taking the limit, which is easy enough to do. And you see, we've automatically ended up with the input impedance in factored pole zero form, because those factors were just dealt with in one by one anyway. So what the frequency response does to the application of the theorem is you just treat a pole or a zero just like any other factor in the A. If it doesn't contain Rs, it cancels. If it does contain Rs, you just get a new corner frequency, that's all. So it's still pretty easy. Now, if you want the inside input impedance, you can take the other limit in the answer we just got for the outside input impedance. And again, you take the other limit, which is Rs goes to 0. You just do that, factor by factor also. The midband part of it we already did. Just takes away the Rs from inside the Rim prime. Leaves you Rim. Look at the two corner frequencies. The omega 2 in the numerator is the original omega 2, which still has Rs in it. So when you take the limit of Rs goes to 0, you get another new corner frequency. Omega 2 as Rs goes to 0, which is the original omega 2 with the entire second term absent. Because if Rs goes to 0, it kills the parallel combination. So you're left just with the R parallel RE1. So there's another new corner frequency that comes from the numerator. When you look in the denominator and take the limit Rs goes to 0, Rs is already limited out because you've already let it go to infinity, so it's gone. So nothing else happens if you let Rs go to 0 when you've already let it go to infinity. So the denominator factor stays the same. So you again get it automatically a factored pole zero form by using the other version of the theorem. Now notice what would have happened, just to look at an alternative. Suppose we'd had only the theorem for the inside output impedance. Then we could have derived this one directly. And then suppose we'd wanted to find the outside input impedance, but we didn't know about the other version of the theorem. What you would have to do is take this, which has got a pole and a 0, and you would have to add Rs. And to get the result in factored pole 0 form, you would have to cross multiply, add the powers of S, and refactor. Not that it would be that difficult in this case, but obviously a longer way, because you have to reconstitute separate pole 0 factors, whereas by using the modified version of the theorem, you get both results immediately in factored pole 0 form. Well, that's all pretty easy. I'll suggest another example you might want to play with yourself. Go back to the other example circuit we've used a lot, the lag lead network, and find the input and output impedances of the lag lead network using the theorem, starting with the voltage transfer function. I won't even bother writing that down, but obviously you can set up that problem. You've already worked it out using the extra element theorem to find input and output impedances, using the capacitor as an extra element. Now here's another way to do it. Use the voltage transfer function and the input and output impedance theorem. So without stopping for that diversion, let's go back to this case and do one more, which I'll also leave for you to do later. And that is, let's forget about the C2. And instead, let's put the two coupling capacitors in. The C1 at the front end, C3 at the back end. So once again, we can practice the extra element theorem to find the modified gain expression to account for the C1 and the C3. Okay. Again, we can do it all mentally. The reference condition, of course, is C1 and C3 short circuits with the same mid-band gain that we had before. So the reference gain is the high frequency gain, and we'll use the version of the extra element theorem for an extra series element to put the C1 in. So the process is, again, doing it all mentally. You replace the extra element by the independent source, and you calculate the resistance, RD, looking in under conditions that the V1 is 0. So looking in place of the C1, you're going to see RS to ground in this direction, RB parallel the reflected RE1 to ground in the other direction. So that's the value of RD, which together with the C1 eventually is going to develop the pole. So that's the omega 3. And it's an inverted pole because the reference gain is infinite frequency. Now, in fact, this is, of course, the identical problem we did earlier as an example, where we put this capacitor in. So that's the same result. And the Rn is found by replacing the capacitor with the independent source, restoring the V1, twiddling the two until the output nulls, propagate the null back, and again, it doesn't matter how far away the output is, because it's going to propagate back all the way back to the collector and the emitter and the base of the transistor, just as it did before the emitter follower was there. So nulled output propagates back to zero base current and to zero emitter current, therefore zero current in RB, therefore zero current through the second source, therefore Rn is infinite, and there is no zero that comes in the transfer function, which, as we already also saw previously, is an answer to be expected anyway, because the two sources are directly in series, and the only way you can get a null at the output is for the two sources to cancel each other directly, which means you have zero current everywhere. So you get an inverted pole as a result of the C1 and no inverted zero along with it. Now you do the same thing for the C3. In fact, it's in a similar position. So you can tell in advance you're going to get an inverted pole from it, but no inverted zero. If only because at zero frequency, the C3 opens up and disconnects the output from the input, so the gain is going to have to go to zero at zero frequency. To follow it through in detail, it's exactly the same sequence of steps. Replace the C3 with an independent source. Find the driving point resistance RD if the V1 is 0. If the V1 is 0, this generator is 0. So nothing happens to the left of the R3. So when you look in, you're going to see RL to the right, plus to the left, R4 parallel RE2 plus the reflected R3, which is this expression at the bottom. Together with the C3, that gives you the inverted pole omega 5. To check that the Rn is infinite, restore the V1, replace the C3 with the independent source, adjust them to null the output, propagate the null back. immediately, if there's null at the output, there's no current in RL, no current through the second source. Rn is infinite, and there is no inverted zero to go with the pole. So we've now obtained two inverted poles, one from each capacitor. Numerically, 240 Hertz and 320. So the frequency response is the reference gain of 36 dB and the inverted pole coming from each of those coupling capacitors. Now notice we put two extra elements in. Why didn't we need the two extra element theorem? Well, actually, you put the two elements in successively, one after the other. Why was it easy to do that? Yeah, they don't interact. That's why it was easy. In other words, the driving point resistances seen by each element were independent of whether the other element was there or not. That's why after we put the C1 in, and we calculated the driving point impedances for C3, those impedances were still resistances, in spite of the fact that there was a reactance already in the circuit, because the driving point impedances were unaffected by the other element. So this is sort of a special case of the two extra element theorem. The special case is if there is no interaction between the two extra elements, the result is the same as applying the single extra element theorem in succession, which is exactly what we did. But notice that wouldn't work if we wanted to put the coupling capacitor and the bypass capacitor in at the same time, because they do interact, which means that once you put one of them in, the driving point impedances seen by the other one will become reactive, depending on the first element, which means you won't get the nice, convenient, immediate pole and zero result. You'll have to do a bit more algebra. That's where the two extra element theorem comes in handy. Well, again, we're not going to do that case here. This also... Okay, what we've done now is, for this especially simple case where there was no interaction between the two reactances, we can get the result by putting them in separately. So we get two inverted poles. So the final step is, now that we have the modified gain expression, you can use the input and output impedance theorems to find input and output impedances in this case. Well, I'll leave that to you to do for an example also. What you expect this time is, of course, both the input and the output impedances are going to be frequency dependent. Okay. Finally, to summarize the input-output impedance theorem, it permits those impedances to be determined directly from the gain by taking simple limits with respect to source and load impedances instead of going back to the circuit model and starting all over. You get some bonuses. If the gain is in fact at pole zero form to start with, so are the results for the impedances automatically. You always get huge simplifications because only gain factors containing source or load impedance are needed for the result. All the others cancel out. Finally, the outside impedance formulas are simpler because only one limit needs to be taken. If you want the inside impedances, you can just take the other limit and the answer you got already. So these are very simple and yet powerful analytic techniques. Give you a lot of useful information for very little work. That's the bottom line for all of these things. So it didn't take very long, really, to go over that. It was a lot less time needed for the input-output impedance theorem than it was for the extra element theorem. Because the extra element theorem required this new concept of null double injection, so we had to spend quite a bit more time going over that. And the input-output impedance theorem required only a knowledge of limits, and even if you're rusty on that, at least you know how to do it. So that wasn't so hard to brush up on that.